Good morning everyone and welcome to the third part of my tutorial to create rack. I was gonna say rack extension. No, these are not rack extensions. These are plugins for rack. And yeah, if you are watching this for the first time, I recommend you to start with my other videos because I'm gonna continue where I left off last time. And what we were doing last time, it was we had the chicken module, which I turned into a filter, into a very simple filter. And what I'm gonna focus this time, it's on show you how the source code is generated by Vult, and also I'm gonna cover how you can debug your code. So okay, if you remember, what actually the Vult compiler does is taking this source code, which is like a simplified syntax and with some handy features, and it translates all the code to C++. But in the case of C++, and especially when we are using floating point operations, the code is pretty straightforward. It looks very similar. So if we compare, let's say, the edge function, I'm gonna try to find the code that is generated by edge, and it's pretty much the same. The only thing that we can see is that every function has the context, and and every function is typed. And let's check where the edge function is used. Actually, it's not used anywhere. Let me try another, like the slew. It's here. So this is the code for the channel. Let me find the same. The equivalent is this one. We're using the slew function here. And the difference is that automatically the compiler is creating the context, inserting the context, typing everything. And as I mentioned before, when translating to C++, the code is pretty much the same. It's readable. There are a few operations which are split into more lines of code. And what can happen as well is that some operations are simplified and some parts of the code that is not used are removed. But this is readable. When using fixed point code, the code it gets actually much more complicated. I try to generate it. So this is not gonna compile immediately, but you can see. Actually, yeah, you can see here that now the operations are completely different. Where we don't see divisions. Now there are calls and the numbers have been turned into integers. It's a little bit more difficult to follow. So what I do, I tend to use the floating point, and only if necessary the fixed point. Let's say in the case where I want to run the code in a microcontroller. But let me show you what it generates for a simple function. If I create the function foo and I just return the same value plus 1, I regenerate the full code, and let's find it. It should be here. So this is the function. It's straightforward. And one important thing that you can see is that the function doesn't have a context, so the input is exactly the same as the Vult code, and the output, and it's just a single output. And when we add context, let's say memory y it's equals to x. for some reason we want to remember the last input, I regenerate the code, and oh, here it is. Now the code requires a context input, and it also generates an initialization function for the context. That way you can be sure that that all your code is set to a default value, because sometimes well, in C++, when you do optimization, when you do high optimization, you have to initialize everything because you are not sure, or you need to be careful to write the values before reading them, because there is no guarantee that the values are going to have a sensible value. If you add a floating point value in C++, a floating point variable, and you use it without initializing it, it can have any number, and that can produce a crash in your program. So to simplify that, Vult generates initialization functions that are gonna put everything in a default value, and you can start using them. Okay, this was case with the memory. The next thing that we can see, what if I return two values? What's generated? In this version of Vult, which is 0.3 something, the way the multiple outputs are returned, it creates a tuple structure, which is it's like a single structure that can hold two values. So what we can see is that the output is passed as an argument, and then our function is calculated. I mean, we perform the operation that we wanted, and then we set the values to this tuple, which is later assigned to the output. So this is a very straightforward pattern to return outputs, and it may look here that it's allocating more memory that's needed. Like first allocates the tuple and then makes a copy. But I've seen that when you use optimization level 2 or 3, this operation is not performed, and everything is written directly to the output. So I actually don't care about the performance of this code, because it's quite good. Then yeah, and that's it. That's basically all you need to do to know to interface code. And the nice thing is that if you write only like all your DSP code in Vult code, and you have an entry point, like in this case, you don't need to care about how the rest of the code is generated. You can just use it. For example, yeah, in the chicken module, what we were doing is like declaring a processor, initializing it, and after that we just need to call the process function or some of the auxiliary functions, like to set the values, and that's it. And here we can see the multiple return value. And as I mentioned in one of the previous videos, this way of returning values has changed in the latest version of Vult, which I haven't released. Then the latest version, it produces better code for JavaScript and Lua, but it's practically the same. You just need to change. If once the version 0.4 is released, you will have to change very little parts of your code. And yeah, if you don't remember, most of the Vult code relies on these two files, the Vultin, which need to be matched to the version of the compiler, because sometimes I make changes here or improvements. So when you download the Vult compiler, it usually comes with the matching source code, which is the Vult runtime, which is it's quite simple. It just have auxiliary functions. And in order to compile it together with with the chicken project, what I had to do, it was modified slightly the makefile, so it will accept .c files, which is the built-in is it's written in C. This is the only change that I had to do. So if I let me clean. If I compile this, we can see that this line compiles the Vult engine, which is the chicken.cpp. This compiles the plugin, which is the VCV rack. This is also part of the VCV rack plugin, and then we compile the Vult runtime. And the last thing here is generating the shared library, and then we can see that yeah, all this is just to prepare your plugins for distribution, and lastly everything is installed in my documents rack plugins directory, so I can use it. So all this part is pretty straightforward, and if you have any questions regarding this, in the Vult page, I have a link to Google Groups for the Vult language. It's not very active lately, but if you send a question there, I will receive an email and I can answer back. Okay, next thing that I wanted to show it's how to debug. So, I mean, the best way, I mean, the debuggers are very useful, but usually I try to avoid them as much as possible, because it requires you to work under certain conditions. So let's say that we have a bug in this source code. How will I debug this code? Let's say I'm going to enable this trigger. Actually, I'm going to leave it like that. One thing that I usually do before running a debugger, it's to create a fake output. I'm going to create here a hidden output, which is only present while I'm debugging. So I'm going to call it hidden output. And with this hidden output, I'm gonna place it somewhere. This is my hidden output, and I'm gonna place it randomly. So it's gonna be on 40. Yeah, let's see where it shows up. Okay, so here I'm gonna move it a little bit more to the side. I'm gonna take 60. Okay, so this is my hidden output, and in the code that I release, this is not gonna show up, but I can use it to output signals, and with these signals I can use them in the scope, or I can also use the min max to measure the values that I'm outputting. I'm gonna give you an example. So I have that hidden output, and what I'm gonna do, let's say that I want to check that this edge is happening. So for some reason, my sample and hold, okay, this is the previous code that required a trigger, and for some reason I don't see that there is a trigger occurring. So what I will do is I take this signal, the trigger, I'm gonna output that signal as in the process. Let me regenerate the code. What did I do? Seems like I hit a bug. Strange. Okay, let me take the output, the regular output, and use this one. This is strange. Okay, this works. This works, but this didn't work. Let me check why. So I'm gonna add an explicit annotation. Actually, don't remember my syntax. Okay. I actually have no idea what's happening. So I don't know why I cannot see this output. Yeah, I don't know, maybe it seems like a bug that I have in this specific version because I haven't hit this one before. So what do we do? Let me just take the signal and see what happens. I'm gonna output this signal here. This is bad. Seems like it doesn't like Boolean signals. Okay, there's a way that I can still see it. So if trigger, I'm gonna check if I still have that problem in the old, sorry, in the new version of the compiler. Yeah, so I think it has to do with outputting a Boolean. I'm gonna fix it in the newest compiler, and I hope never hit it. So I'm gonna try to make, and now the problem is that this returns 3 arguments, and here is telling me what is the type of the return. So I need to change that. Here, this is my output, and I'm gonna take the value that I'm outputting, which is the field number 2. Actually, I want to see the exact value, and this is gonna go into the hidden output. That's it. So let me use an LFO. I'm gonna insert the signal into the clock, and my hidden output is gonna show me the value, and I can see. Let me go as slow as possible. Yeah, I can see that there are in fact tiny pulses. That means that my trigger, that means that my trigger, that this value it's working. Therefore, I can my error may not be here. And what if I want to look other stuff? I don't know. Let's take. I want to see what's the frequency value, the W that the filters are using. I will just output it here. Let me compile again. And I have the W value, which I can measure with the min max module. So if I change this, I can see what value I'm setting. You can also read it here, but yeah, it's more clear if we use this one. So before debugging any code, I try to do this approach first, because sometimes quite often it's easier to see if the values are changing or not, and in which situations and for which inputs we get. We can see the waveforms that we are getting, but sometimes the problems or the bugs are hard to catch or just happening under certain circumstances, and we need to insert some control inputs. In that case, what I will do, it's I'm gonna keep this one, and since it's my hidden output, yeah, if you want to hide it, you just have to comment out this line. If we install it, we don't see the output. Everything is still processed, so you can use some like defines or some stuff to hide, to disable completely the source code. But in this case, the operation is very simple, so it doesn't matter. I just hide it, and it's fine. Next step, if I want to debug a problem that happens under certain circumstances, what I will do, or one nice thing about the Vult code, is that everything it's isolated. So this code here doesn't require anything else apart from the runtime, of course, to compile and run. So instead of saying I'm gonna compile my plugin, then I'm gonna launch rack with debug mode, and then I'm gonna try to hit a breakpoint in my code, I find that more complicated, and I prefer like splitting the problem into smaller chunks. So what I'm gonna do instead is creating a small program that I can launch in debug mode, and that this small program doesn't have anything to do with the rack code. So it's just a tiny executable that calls my Vult code under these circumstances, and I can debug it. So to do that, it's not straightforward. It's not complicated, but we need to mess a little bit with the make files. So if you're making a plugin, you practically need to define only these things, and rack, or the source code of rack, makes the whole thing here. So you don't need to care. So this is quite flexible. You just need to provide your sources, like you don't even need to modify this. But yeah, you just provide your sources, and the rack makefiles are gonna adapt and create your plugin without you having to do anything. But in our case, what we have to do it's some manual work. If you have never used makefiles, yeah, I try to avoid them as much as possible. And I usually use CMake, which is simpler and it works fine in all platforms. But yeah, let's try to fix this thing. So what I'm gonna do, I'm gonna create a folder where I'm gonna put my source code. Make the debug. So here is my debug folder. What I'm gonna do here, I'm gonna create a main.cpp file. That's my file. And here I'm gonna write the program that I'm gonna use to debug. But first I'm gonna make a hello world main. Not even a hello world, I just want to check that it compiles. So what we have to do now is that we have to compile this file and then we have to link to create the executable. And to do that, we have to create a new target. This is going to be my target called Debug, and it depends on my file called debug/main.cpp. So what this line says is that every time that this file changes, I want to trigger this set of actions. What I'm gonna do is actually I'm gonna like copy one of these calls. This is actually doing the same, but in a much more generic way. I'm gonna copy this line because make I think I don't have tabs in my editor, and make cares about the tabs. So I'm just gonna copy this line. I'm gonna paste. No, I copied only that part. Okay. Now I have the correct spacing in my file, and what we're gonna say here is like compile with these flags. This is the flag to compile, and I want to output a file called I'm gonna put it in the build folder, which is in the same place where all the other hack binaries are. That way, when I do make clean, it deletes it. So I want to output this file, and the file that I'm gonna compile is this one. Let's check if that works. So now I have my target called debug, and I'm gonna do make debug. So the call seems correct. It's calling the compiler with the same flags as my plugin in Rack, and it should generate this file. Let's check if it was generated. Yes, it's here, and this is the debug information. Okay, so next thing that we need to do is linking the file using the sources of generated by Vult and our main application. To link, I think, let me try to find where is the link. Okay, I'm gonna I think that we need something called LD flags, which is the linking flags. I'm gonna use them and let's see what happens. So this time we're not compiling, so we remove the -c, and we are gonna output. Our output is gonna be an executable called main, and we want to link the object file that we generated in the previous step. Let's see if it works. It actually links. Let's try to run it. Or maybe this one is it's specified that it requires that it's generated in a shared library. Let's check. Yeah, okay, so I cannot use this. Let's see if it works without passing the flags. Okay, this seems to work. I'm gonna make a hello Vult, and I need to include the standard library, and that should be enough. Make debug. Okay, this works. So yeah, right now we have specified that we are creating a binary file using the output of this, but we also need the objects. So what we are gonna do, I want to make it simple. No. I want that every time that I change the code, every time I change the sources, this rule needs to be triggered, or the opposite. If I want to recompile the debug, it is gonna check if the sources have changed. Which sources? Like all the C files right now. I don't care. Then I'm gonna link the object files of the Vult generated code, which is this one, chicken cpp.o. So I need to give it as well, which is in build src chicken.cpp.o, and I also need the Vult runtime, which is the same location. So it's called built-in, and it's a C file. Let's try this. Okay, it compiles and it's linking as well those files. That means that I can use inside this program, I can use the generated Vult code. Chicken.h. So she'll be able of compiling. Okay, it cannot find the file because I haven't provided the include. So when compiling this, I need to provide a flag to include whatever is in src. Okay, now it works. Let's call, I want to call this function process. So I need to follow the instruction that I had mentioned. First, you create, I'm going to remove this line. First, you create a type, process type, and it's called processor. Then we initialize the type. And let's compile and see if this works. Yes, it works. Now let's call the code int I equals 0. I don't know. Let's call it only 100 times. Do I plus plus. Simple loop, and we are gonna call chicken process, providing the context, which is processor, and then we need to provide inputs for clock. We don't have a clock right now. As modulation, I'm gonna give one signal. I'm gonna call it X. I'm gonna declare it later. For mod 2, I'm gonna give 0. And now I need the output, which is this tuple. I'm just gonna copy it from here. So it's this. So I need to declare an output. And I haven't declared X. So what I'm gonna do with X, I'm gonna create a very simple ramp. Actually here, this needs to be floating point values. This one as well. Okay, that's a ramp. Let's compile. Okay, seems to be fine. So I have my program, and just to make sure it works, or that it doesn't work, I'm gonna print the value of X that I'm generating, like that. Yeah, it's working. So 100 times here. Yeah, seems to work. And let me just give 200 values to see. So okay, it grabs, reaches to 0.99999 and it grabs to 1, so this signal is fine. So this part is working. And what I can do, it's just for testing, I'm gonna take from the output dot field 0. Yeah, let's see what it outputs. Hey, so problem, we have a NaN. The first time we call the function, there is some invalid operation which is producing a NaN. Let's try to find out what's happening. And let's configure the debugger. So in Visual Studio Code, you have this section which is the debug code, and you need to add a new configuration. So it's adding a new configuration, and it's gonna be a C++ launch, and we're gonna call it chicken debug. The type is this one. We're gonna launch the program, or the program that we're gonna launch is main. We don't have arguments. Let's stop at entry. So when the program starts, I want it to stop automatically. Then everything else is by default. And that's it. We have configured the debugger, and I'm gonna try to launch it. And if everything is correct, it should stop at the beginning of the program. Yeah, it stopped. And if I start stepping in the program, then the first thing that I see is like it's jumping. It's not executing the program in order. And why is that? It's because we are compiling. Oh, and if you saw, we don't have the values of the variables. So it says invalid load address. So this is because the optimization is switching the order of the operations in our program to make it more efficient, and at the same time it's just getting rid of things that are not necessary. Then in order to fix that, we need to compile. Let me close these two terminals. So when I do this make debug, we can see here, down here, that it says 03. So that's the maximum optimization. And yeah, we don't want maximum optimization. We want zero optimization, so we are able to follow operation after operation what's happening with the program. And this is actually defined in the rack code. So I need to open this inside the rack folder, the compile .mk file, which is used when compiling. And here, optimization, I can see that it's 03. I change it to 00, which means no optimization. I just save it. I'm gonna make clean to make sure that all the code is recompiled with the new flag. Make debug, and what happened? So that seems like I have some strange issue with the way I did the make file. So this one is trying to file. Try to compile this part first. Okay, so I have some strange dependency. Okay. So I know what's happening. So when I did make debug, I didn't specify that I want to first compile the other part, the other files, and compiling these files creates a build directory which didn't exist. So there is no build directory. Therefore, I haven't created it yet. It is created by the plugin infrastructure of Rack. So instead of relying on the sources, I think that Rack generates this one, which is called objects. So I can use objects instead, and that means in order to create this, make sure that the object files have been generated. Therefore, and that is gonna make sure that the build directory is there. So I'm gonna make clean again, make debug. Okay, and now you can see that first is compiling all the other files used by Rack, by the Rack plugin. Now it compiles my main and it links it. So, and we have optimization 0, as you can see here in all files. Okay, so now that we have optimization 0, I'm gonna launch my debugger and let's see how it behaves. Actually, I don't want it to stop anymore at the beginning. To change that, I'm gonna say stop at entry false, and I'm gonna stop it at a breakpoint. So just mark a breakpoint and launch it. Okay, so it stopped here, and let's get into the code. So the first thing, we see that it's calculating Q, and now we have a value of Q. And here we can see what I was telling you before, that when the program starts, the values can be with any random value. For example, W, it has this value because it haven't set yet. We set W to 0 because that's the value that we get from the knob. Let's get into the code of the low pass. We calculate cos W, then we calculate alpha, and here's the problem. So alpha, we have a division by 0, so we see that when we start, the Q value cannot be 0. If it's 0, this is gonna produce immediately a NaN because we are dividing by 0. Therefore, Q cannot be 0. That's a bug in our code. And yeah, so after that, everything that is calculated with alpha is gonna be set to NaN. For example, here we can see all the values of the context, and all of them are NaN. So this is a problem, and it is something that I didn't translate it very well from the original source code. So this one cannot be 0, and I think that the minimum value should be like 0.5. Don't remember. So if I do this, if I set it to 0.5, let me close my debug terminals. Okay, first I need to generate the source code of Vult. Compile. Run the debugger again. So Q has 0.5, W is 0. We start executing the code of the filter. Alpha is 0 now. It's not none. We calculate all the coefficients, and then we can see the values of the coefficients. We execute the bytecode function. So it seems to be working now. Let me execute it. Okay, but everything is 0 because we have not set the value of the nop1. So to do that, it was chicken not process. It was set nop1 to the processor, and we're gonna give a 0.5 value. Actually, we don't need to set it every time. We just need to set it once here. So if I compile and I run, okay, now I see that the values are changing, are different. So that was a bug in this code that will make the filter unstable. Let's corroborate it. I'm gonna leave it as it was before. I'm gonna generate the code, install the plugin. I'm gonna open this. Let's insert a signal. I'm gonna take triangle, and I'm gonna set the resonance to 0. So, okay, yeah. Now it triggered the bug. It went to infinite. So we have plus minus infinite, and it's not a number. So yeah, the bug happens if we put the resonance to 0. I'm gonna close it. Let's launch it again and try it. Yeah, immediately it goes to infinite. So that's the bug. And I'm gonna put back the fix. Yeah, working fine. The saw wave, increase resonance. Yeah, so it's working fine. It's not getting unstable in any of the extremes. So yeah, it seems to be working. We fixed a bug. And yeah, one more thing that we can do while we are here, I'm gonna call this, I'm gonna remove the print. So this is gonna call the processor, and I'm gonna run this 200,000 times. So make the debug. Runs quite fast, even without 0. But in most of the platforms you have tools to profile. For example, here in Mac it's instruments, a time profiler. In Linux I use perf. In Windows I don't know. I don't usually develop directly on Windows. I just profile in other platforms and let the code be compiled in Windows, because yeah, I don't know, it's not very friendly, developer friendly, unless you use Visual Studio. So I'm gonna create a new time profiler, and I'm gonna select a new target. So I choose a target and I go to where my application is, which should be sitting home. Oh. Well, it's users, it's Leonardo, and I have this thing inside my development folder. Then I have it in rack folder, plugins, template, and here is the main. And I don't need any arguments. I don't need any special working directory. I'm just gonna select it, and then I can run the profiler. And yeah, it was quite fast. And we can see here where like the timing, what's consuming time in my source code, in my code. But okay, consider that this is O0, this is optimization 0. So what this what this thing shows is that 80% of the time is consumed by the main function. Let me make it last even longer, like this. It's quite fast. Okay, now it's taking some time. I'm gonna record. Let's see the results. So 98% of the time is consumed by the process function, which makes sense because everything is done here. And inside this one, we are using 64% of the time in the low pass, which is the filters. What is this? This seems to be a system function related to the mathematics library. So this could be the cosine function, the sine and cosine. I think that they are used. These two come from the M library, so I guess that is that. Okay, then we have 25% used by the byquad function, and that's as deep as we can get. Well, actually we can see the assembly code, but it's not very useful if you don't know how to read it. But I think that this one is the sine and cosine, because they live in the math library. And so yeah, using this kind of tools, the profiler is very good for finding the hot spots in your code. But sometimes you don't get too much information, because if you do O3, so the maximum optimization, actually let's do it. So I change the optimization in this file from the rack code, put it back, I do a make clean, make debug. So everything is compiled with the maximum optimization. Going back here, and so before it was taking 1.38 seconds to run everything. Now let's see how much it takes with the O3. So now it took 0.56 seconds, so it went almost 3 times faster, from 2 to 3 times faster. And we can see, yeah, that still this function from the math library are used, and 73% is spent here. And that's it. That's all what we see, because what happens is that some of the functions have been inlined. For example, it seems like the low pass filter has been inlined into the process call in order to optimize, and we don't see anything else. So this should be the assembly code of our whole process function. Yeah, and we can see here the calls to the cosine and the sine. And yeah, based on this, I mean, this is a very simple program. If you do the same process and run it on your plugin, and don't use O3, maybe use O1 or O2, you will be able of seeing the functions in which your program is spending a lot of time, and you may find that one of these functions you have written something dumb, and if you just change it, rerun the profiler, and then everything becomes faster. So that's it. That's all that I wanted to cover with this video. I hope it's helpful for you to know how you can debug and profile your programs. And yeah, sometimes you cannot catch an error with using this process, but because it only occurs when a certain input from a certain module is triggered. And in that case, it's also possible to debug your shared library and load it directly with Rack. But I don't like that approach that much, because I mean, I tried step by step, and if I catch the error this way, for me it's much simpler. You have a more controlled environment. The next level of debugging, I don't use it at all. I usually catch everything here, but sometimes it's necessary. Yeah. So that's it, and this is the last video that I'm gonna make in the VCV plugin development. I mean, for now, if there are some other topics that are important, I may consider making another shorter video. And thank you for watching this. Goodbye.